To everybody, it's time to start our session. I think where is Echo? No? Okay, anyway, so let us start our meeting, our morning session, and in the beginning, 5 minutes for Professor Studenikin. Please, yes, yes.
Well, first of all, found. So indeed, I just recall. I recall that we are at this 21st Lomonosov conference, and within this conference, we are organizing the 15th International School on Neutrino Physics and Astrophysics to celebrate the 110th anniversary since the birth of Bruno Pontecorvo that was celebrated on the 23rd of August. And let me say a few words about Bruno Pontecorvo. I would like to recall that tomorrow evening at the end of our sessions, there will be a movie for 1 hour in English dedicated to Bruno Pontecorvo, his life and his very important contribution to fundamental physics, and in particular to neutrino physics. So I would recall really that Bruno Pontecorvo is the author of the most important and exciting result, probably not only in neutrino physics, but in fundamental physics. Just in the year 1957, in his 2 papers, one is referred here, he introduced the phenomena of neutrino mixing, and at that time, he just showed that as a result of this mixing, there will be neutrino oscillations, exciting phenomena that we are studying for many, many years. And a lot of presentations of this 21st Lomonosov conference is dedicated directly or indirectly to the studies of neutrino oscillation and the mixing effect and the effects that are related. So in this preprint that was published in Dubna, 3 pages only, we can find the following words: neutrinos in vacuum can transform themselves into anti-neutrino and vice versa. I would like to recall that at that time there was notion of only one type of neutrino and correspondingly one type of anti-neutrino. So there were 2 species of neutrino and anti-neutrino. The second neutrino, mu neutrino, was discovered in 1962. Okay, and Pontecorvo spoke about 2 possible neutrinos and communication between this. This means that neutrino and anti-neutrino are particle mixtures. So this is an introduction of effect of mixing of neutrinos. And then he go ahead. So, for example, a beam of neutral leptons, I mean neutrinos, from a reactor, which at the first consists mainly on anti-neutrinos, will change its composition, and at a certain distance from the reactor will be composed of neutrino and anti-neutrino in equal quantities. So it means that this is a prediction of result of effect of mixing and oscillation. So just in this very short half-page statement, there are 2 discoveries: first mixing and then oscillation effect. So, and we are very proud that Bruno Pontecorvo for 20 years was the staff member of the Moscow State University, and he headed the department of particle physics here. And also, of course, we know that from 1950, he moved from Europe to Soviet Union, and he has a permanent position in the Joint Institute for Nuclear Research to the very end of his life. And I'm sorry that this is in Russian, but I think that you know this. So a reasonable contribution, exciting contribution of Pontecorvo. First, in 1946, he just put the question of observation of neutrino on a practical level, and he predicted the so-called inverse beta decay process as a process that can be used in order to discover the existence of neutrinos. Then he introduced and proposed where to find these neutrinos, where neutrinos could come from. And he just stated that this is neutrinos and neutrinos from reactor. And he go ahead, he proposed a particular realization of this inverse beta decay process with chlorine, neutrino, argon, and electron. So this is the basis of the radiochemical method of discovery of studies of neutrinos. And these three ideas were implemented by other people. 1, 2, by Ranes and Cohen, who just discovered for the first time reactor neutrino in 1956. Then 1, 2, 3 ideas just for registration of neutrino from the sun, and it was discovered by Davis in the middle of 60s. So that the flux of neutrinos are more or less about 3 times less than it's expected by the standard model. So solar model. And then also he predicted that probably neutrino mu, neutrino E are not the same particles. So, and once again, I would like to advertise that tomorrow we have a movie, Maximovich, the story of Bruno Pontecorvo. So here at the Moscow University, we follow the traditions in the studies. I don't know how to. Okay. So here we establish the Bruno Pontecorvo laboratory on neutrino physics and astrophysics, which have to accumulate all research in neutrino physics and also educational programs. And so we are trying to follow these traditions that were formed here at the Moscow University together with activity of Bruno Pontecorvo in joint theories of nuclear research in studies of fundamental properties of neutrinos. Thank you very much.
Thank you very much. Wonderful, very nice introduction. So let us move ahead, and all day today, I'm in plenary session dedicated to neutrino physics, and it was a very nice introduction again. So I would like to ask all speakers to be on time and to keep time, and 20 minutes for talk plus 5 minutes for discussion and question. So first presentation will be given by Grigory Safronov. Recent results from Baikal-GVD neutrino telescope. Я покажу 5, 1 минуту.
Hello, I will talk about the status and results from Baikal-GVD neutrino telescope. So Baikal-GVD is a cubic kilometer scale neutrino detector being constructed in Lake Baikal. Collaboration consists of 11 organizations from 4 countries, and the leading is from joint the status and recent results. So the main physics motivation behind the large volume neutrino telescopes is the study of high energy phenomena in our universe. So we know that the range of measured cosmic ray particle energies extends far beyond the LHC energy, so which is an evidence for the existence of cosmic systems which accelerate particles to enormous energies. However, the direct probing of such process is a complicated task because cosmic ray particles are deflected by galactic magnetic fields, so they do not point to their sources. Very high energy photons are absorbed due to interactions with cosmic microwave background, and neutrino can actually provide a direct probe because it interacts very weakly and it does not lose the direction to its source. So neutrino can provide a direct probe of energies and location of high energy cosmic sources. So here are some examples of cosmic ray, possible cosmic ray acceleration sites. These are active galactic nuclei. Actually, this can be divided in few types of systems, like the one with very strong gravitating object, like black hole in the middle, and accretion disk, and relativistic particle jets. So systems of that type are like active galactic nuclei or tidal disruption events, which is the consumption of the star by a massive black hole. So it also forms system of that type, but for a shorter period of time. And also neutron star mergers, which are also transient events existing just for some short time. And also another type of systems is supernova remnants. It is a shock wave propagating in space, and the border of this shock wave acceleration can occur. So for example, such sites, supernova remnants can be, there are many of these in our galaxy, so these are good candidates for galactic sources of high energy particles. And also starburst galaxies, which also involve a lot of supernova activity, can be sources of energy particles. So high energy neutrinos are can be produced in the vicinity of these acceleration sites in of PP or pre-gamma interactions. Also, neutrinos can be produced rays along their propagation through the universe, which is the Grazin-Zatsepin-Kuzmin effect. And also they can be produced in Earth atmosphere. So at this plot, there is a spectrum of various neutrino sources at Earth. So, and the region of interest for large forward neutrino telescopes is the largest energies extending from hundreds of GeV to beyond PeV energies. So this includes the atmospheric neutrino spectrum, the astrophysical neutrino spectrum, and we just briefly touching these cosmogenic neutrino, which are due to Kouzakov effect. But for detection of these neutrinos, much larger telescopes are needed. So this is the neutrino telescope network available so far, not available, but being under construction mainly. So the largest telescope is IceCube at the South Pole, which is 1 cubic kilometer. Also, there is our telescope, Baikal-GVD, which is largest telescope in Northern Hemisphere. Currently, it's already 0.5 cubic kilometers. Then there is KM3 telescope under deployment in Mediterranean Sea, and also P1 telescope in Canada, but this is just a prototyping stage. Also, there are discussions currently of building telescope in South China Sea. So the common, all these telescopes, they share the detection principle. It's the sparse array of photodetectors in natural water reservoir, and they detect churning of light from charged particles produced in the interaction. And we distinguish two event types. It's track event. It's charge current interaction. Mainly it's muon neutrino. Such events have very good angular resolution up to, well, say down to 0.3 or even lower actually, but they have very poor energy resolution. And also for such events, we have an increased sensitive volume of detector due to muon propagation range. And also there are cascade events, which on the contrary have moderate angular resolution and very good energy resolution. So the main backgrounds to such measurements are atmospheric by the cut on zenith angle. So we basically look at the upgoing events, so events from below the ground, and also another another background for us is atmospheric neutrino. So that's on the one hand, it's a standard candle for the performance. So we validate our Monte Carlo with that. On the other hand, it is background to all astrophysical searches. So the atmospheric neutrino spectrum is dominated by muon neutrinos, and the astrophysical neutrino diffuse flux manifests itself as an excess of neutrino events over the atmospheric neutrino spectrum, which and this excess starts from somewhere about 60 TeV or so. Here are some key results in high-energy neutrino astrophysics. So the astrophysical neutrino flux is established with very high significance. It's well above 5 sigma already by the IceCube collaboration. However, there are no neutrino sources, established neutrino sources above 5 sigma. However, there are 3 very good candidates which are actually considered as neutrino sources. It's Blazar TXS 506, Safer-2 Galaxy NGC 1068, and also recently IceCube published the observation of diffuse flux from the galactic plane at 4.5 sigma. However, these source candidates do not explain the majority of the neutrino flux, astrophysical neutrino flux. So it's deployment of new telescopes and enlargement of existing telescopes is very important to resolve the diffuse flux origin problem. So now to our experiment. It is located on the northern shore of Lake Baikal, on the Baikal railway station, Ivanovskaya. Telescope itself is 3.6 kilometers from the shore, where the lake depth is constant, so it allows almost unlimited expansion. The water absorption length at the site is about 21 to 23 meters, and the distinct feature of this location is the ice cover of the Baikal Lake, which allows us to deploy the detector during approximately a month and a half period in February, April, so which is very convenient. So that's the current detector status. It consists of 13 independent detectors, which are referred to as clusters. And each cluster consists of 8 regular strings and also one additional string, which is instrumented with with lasers, or and for some clusters also with optical modules. Well, there are 2 partially built clusters. It's cluster 12 and also cluster 13, which is an experimental cluster with a new data acquisition system, high-speed data acquisition system, which is a basis for future telescope expansion. So we analyze events both in a single cluster manner, considering each cluster as an independent detector, and also combining events from different clusters, which we refer to as multi-cluster events. So these are basic detector components. It's a string. It carries 36 optical modules distributed over 525 meters. Each optical module includes 10-inch high efficiency photomultiplier. The vertical step between optical modules is 15 meters. So for time calibration, we use light emitting photodiodes in each optical module, also beacons of such diodes, and also we use lasers between the clusters, and the calibration precision is about 2 nanoseconds. Also, we have the geometry calibration system. It's a system of acoustic beacons located at each string. There are 5 beacons, like one is with constant coordinates, and also 4 beacons which are tilted according to string motions. And the positioning precision with this system is about 20 centimeters. An event is read out from the cluster if the coincidence signal is found on neighboring optical modules, and the event frame is 5 microseconds. So, and actually mainly in this event frame, we see the lake noise. So this is an example of event, the track-like event. And here are the hits shown in color, and mainly these are hits due to lake water luminescence. So the typical pulse rate due to this luminescence is from 20 to 100 kilohertz, depending on the depth or the season. So this is 1 photoelectron. Typical charge deposition for these pulses is 1 photoelectron. So here one can see the variation of rate of this noise with time. So typically in middle of summer, the noise is much larger. So this is the challenge for our Monte Carlo simulation. So both our reconstruction channels start with the suppression of this noise. And we actually also we are developing the machine learning based algorithms for this noise suppression. So for the actual reconstruction, the time, location, and deposited charge of each pulse are used. So this is an example of the like event reconstruction. Actually, this is the same event, but after the noise cleaning algorithm and the track fit. So we have an angular resolution for tracks from 1 degree down to 0.25, depending on track length. And the energy resolution is factor 3 at 100 TeV. So, and for cascade reconstruction, so this is the example of cascade event reconstructed in 2022. So the resolution is about 3 degrees, depending on energy, and the energy resolution is from 10 to 30%, depending on the energy and cascade location with respect to the cluster. So now I will talk about our results. Our first track-like neutrino candidate sample was selected in 2019. Its analysis optimized for low energies. So it's atmospheric neutrino, and it is compared to atmospheric neutrino simulation. And results obtained are in very good agreement with the atmospheric neutrino simulation. So that's first validation of the Baikal-GVD performance. So event analysis improvements. So currently we proved sensitivity by more than a factor of 2 with a lot of improvements. And currently the massive data reprocessing is ongoing. So here we show some preliminary results. It's a high energy event observed in 2019 data. It consists of 30 hits, and the estimated energy is about 100 TeV. And this event has a very high probability of astrophysical origin. So that's one of the first events of high energy events observed in track-like channel, and we hope and we expect more of this with this reprocessing. So stay tuned for new results here. Also in track channel, we developed the multi-cluster analysis. So this is an example of one of first multi-cluster events. So the cascade analysis is more advanced. So the majority of Baikal-GVD data were processed with the cascade reconstruction algorithm. So it's 4 years data set from 2018 to 2022. And the search for diffuse flux was performed in this data. So the analysis consists of 2 types of selection. It's all sky analysis, where no zenith angle cut applied. So it has some stricter cuts on energy. Energy is required to be above 70 TeV, and the number of hits above 19. So and the significance of diffuse flux in this analysis was found to be 2.2 sigma. And another analysis is the cascades. So this one potentially has better sensitivity due to atmospheric ion background suppression. So here the zenith cut on the cut on zenith angle is added, and also cuts on energy and number of hits are loosened. So, and in total there were 11 events selected, while the expectation from the atmospheric background is 0.5 events from atmospheric muons and 2.7 events from atmospheric neutrinos. So the total significance of this flux was found to be 3.05 sigma. So in the same paper, we performed the fit of the diffuse flux spectrum. So here is the summary of the fit. It's shown in red, and it is compared to previous fits by the IceCube and Antares. In general, our fit is in agreement with previous results. So to the bottom line of this paper is that this is the first non-IceCube evidence for the diffuse flux of astrophysical neutrino above 3 sigma. Also, there is an update to this analysis for season 2022. It's a 10 cluster detector, so the significance is increasing slowly. That's the summary of the cascade map, cascade sky map. So here are some spectacular events, like largest energy event. It's 1.2 PeV. Sorry, this is a misprint. Also, there is a spectacular triplet of events near the galactic plane. Here it is shown zoomed. So it is a pretty intriguing coincidence in view of the recent IceCube observation of the flux. Just a few more slides from the galactic plane. So also we have published a paper on the observation of spatial coincidence of cascade of energy to 224 TeV with TXS 0506, which is considered as neutrino source. So we also found that the time of observation of this event was coincided with the increase of this the activity of this source in radio in radio telescope data. We also developed the follow-up program. We follow the multi-messenger high energy events reported by other telescopes. For example, the famous gravitational wave observation in year 2017, the neutron star merger, which was also observed in various other measurements, not only gravitational, but also gamma, optical, and radio. So we set limits on this event. And also we perform an alert exchange with other neutrino is deployed, but so far only in GNR, but we also plan to deploy it onshore to reduce the delay. So far it is distributed, alerts is distributed just internally, but we analyze external alerts from other experiments. So here we analyzed 60 Antares alerts and found 3 correlated cascade events. And also we followed up IceCube AstroTrack events, about 20 per year. And in year 2021, we found a coincidence and published an Astro telegram on that. However, the significance was later reduced. Okay, this is my summary. So our detector has already reached half of cubic kilometer instrumented volume, which includes 96 strings carrying 3,456 optical modules. So our telescope is joining the astrophysical neutrino origin quest. We have validated our performance with atmospheric neutrino flux observation. So in track channel, we select first high energy events. High energy cascade event analysis confirms the diffuse flux at above 3 sigma level. And also we participate in the high energy event alert exchange with other telescopes. Thank you. That's all.
Thank you very much for a very interesting talk. Questions for Grigory, please. Can you show in internet? Also, maybe questions internet. Yeah, I don't see here. Yeah, questions, please.
I have a question.
Yeah, please.
So concerning future plans, is GVD planning to extend more into the low energy, I mean the atmospheric neutrino energy, or the extremely high energy side? What's can you share with us the plan?
Yeah.
Okay.
Yeah, the priority is about 10 cubic kilometer detector.
What's the dimension or the size of the final version in our vision?
Well, it depends on financing. I'm not really sure. I cannot really project, but I think our goal is 1 cubic kilometer for now. But for future, it depends.
Okay, thank you.
Other questions?
Are there any plans to make some kind of deep core like an IceCube?
There are discussions about that, but I'm not yet aware about some practical plans for that.
Are there plans to make, I don't know, like radio telescope surface one, like in the IceCube Gen 2?
Radio telescope.
Yeah, surface.
But yeah, we have water on surface.
No.
So
nearby surface.
nearby surface. No, I'm not aware.
Okay. Thank you.
In the forest.
Yeah.
Okay, okay, please. Maybe last one. because yeah, time is already running out.
Is it possible to measure the flavor ratio of astrophysical neutrinos in Baikal telescope?
Well, in principle, you can distinguish tau neutrinos from muon neutrinos. So to some extent, yeah, you can measure, but I'm not really aware of any assessments into this problem.
You mean the same technique as IceCube is using, yeah, for separation of tau?
Yeah, like double cascade events.
Okay, then let us thank Grigory very much again for his talk.
Yeah.
You look at internet and take questions, I should know. Okay, okay, let us move ahead. Next topic we present Dr. D.Akimov. Worldwide experiment study of neutrino coherent pattern. Okay. What's meant? Yes.
Good morning. First of all, let me express many thanks to our organizing committee for the invitation to give a review talk on experimental study of CEvNS. CEvNS is an abbreviation. CEvNS is an abbreviation of coherent elastic neutrino nucleus scattering, the process which was predicted theoretically almost 50 years ago by Friedman from US and Russian scientists Kopelyovich and Frankfurt, shortly after the discovery of neutral current and neutrino interactions in experiment at CERN. So the effect of coherency takes place when QR is much less than unit, where R is the nuclear radius and Q is transferred momentum. So in this case, the phases of scatter amplitudes at different scatter centers inside the nucleus are close to each other. So they are summed together and the resulted cross-section is proportional to n squared. The CEvNS has never been observed experimentally until recently because of the very small energy transfer to the nucleus in KV and sub-KV region. And the situation is even worse because of a so-called quenching factor, which significantly reduces the signal. So the cross-section of CEvNS processes is given by this formula, where T is the nuclear recoil energy, F is nuclear form factor, and QW is so-called weak charge. Because of this weak charge is nearly equal to n, where n is the number of neutrons in nucleus. So the cross-section is proportional to n squared. On the left, this is the cross-section of known process of neutrino interaction versus the neutrino energy, and you can see that the CEvNS cross-section among them. On the right, you can see the cross-section averaged for so-called pi indicate rest neutrino source versus the neutron number. And you can see the measured points, experimentally measured calibration for cesium and iodine nuclei and for argon. For heavy nuclei such cesium, iodine, and xenon, the typical cross-section averaged for energies for reactor neutrinos is of about 10 to minus 40 square centimeters, and for pi indicate rest sources is 10 to minus 38 square centimeters. So motivation of the experiments. First of all, it is interesting to check so-called standard physics. If the measured cross-section will be different from the predicted by the standard model, it would be an indication of the new physics. So this process also is very important for astrophysics because it significantly affects supernova dynamics. We know that 99% of gravitational binding energy goes to neutrinos. It's also a new tool for study of nuclear structure. The nuclear form factors can be measured by this process, and it's also a new tool for the main drawback of such detectors is the very low target mass. Okay, so the germanium detectors. The COHERENT group from the US proposed to use so-called p-type point contact or PPC germanium detector. Such detector can be produced with very low capacitance, which allows one to significantly reduce energy resolution and energy threshold. The Sun Anafre nuclear power reactor, it turned to be, the energy threshold, it turned to be quite high of about 400 electron volts. After that, the COHERENT group switched to the dark matter search, where the threshold requirement is much softer. The Texona experiment at Taiwan uses the same type of the detector. A detector is placed inside the sodium iodide shielding, and the setup is located in the 28-meter vicinity from the reactor core at 30 meters water equivalent over Boden. So they have achieved about 300 EV threshold with liquid nitrogen cooling and 200 EV threshold with electrocooling. The new gen experiment goes in Russia at Kalinin nuclear power station. The same type PPC germanium detector with a mass of 1.4 kilograms is placed inside a multi-layer passive shield, and the setup is put on a movable platform at distances from 10 to 20 to 12 meters, where the flux is about 4 to 10 to 13 per square centimeter per second. And the setup is located under the reactor. Of about 50 meters of water equivalent. So the run was carried out, and the result is given in this table. I think that more details we will know from the talk this afternoon. So as I understand, the threshold is quite high to observe the CEvNS effect. The another experiment, similar, CONUS, at a nuclear power plant at Brockdorf in Germany, uses 4 1-kilogram germanium detectors at 17 meters distance from the core. And the flux is 10.3, 10 to 13 per square centimeters per second, and threshold is about 200 electron volts. There was 5 years of successful operation, and the group has carried out careful measurements of quenching factor by themselves, and it was shown that it is in accordance to the Linhart model. Unfortunately, they claim that they are still above their prediction of the standard model by a factor of 2. Now the detector, the setup is moving to another site, to Switzerland. The next detector, next experiment, Dresden 2, at Dresden nuclear power plant in USA. The detector is of the same type, with a 2.9 kilogram detector having 200 electron volt threshold. The setup is placed quite close to the unfortunately, practically no overloading. So the group claimed observed standard model predict immunity and almost no shielding against fast neutrons, and there are different shielding during reactor on and off, resulting in big difference in in background level during the reactor on and off. Also moderate energy resolution, more than 150 electron volts, and measured by them is more than by Linhart model. The CONI experiment in Brazil at Angra reactor uses silicon, uses this charge coupled device. So there is a stack of such CCD matrix. It is 3D. It is actually a 3D imaging detector, which allows one to reject electron recoils by tracking and accept only point-like events like nuclear recoils. The threshold is as low as 50 electron volts, and they carried scientific run, but unfortunately the background is very high, and they put the limit of about 70 times higher than the prediction. It allows dramatically improve the signal-to-noise ratio by multiple measurement of each cell charge. So you can see that it will allow one to see single electrons. So it allows one to single electron counting, and will allow to significantly reduce the energy threshold down to 20 electron volts. Cryogenic bolometers are very attractive detectors. So they are sensitive to heat produced by particle interaction in crystal. This is because the phenomenon that at the very low temperature, the specific heat capacitance becomes very small according to a detector in France will be installed 58 megawatt research reactor. There are two options with germanium and zinc detectors with 50 eV threshold. The detectors will be put inside cryostat and inside the multi-layer shielding, and the expected background is so the background is expected well below the seventh effect in 100 eV range. So construction is ongoing, and first data taking will be expected in middle of the next year. The minor experiment in USA uses the effect of Neganov-Trofimov-Luka of phonon amplification and the applied electric field. This allows one to significantly reduce down to 10 electron volts energy threshold. So the experiment is at 3 1 megawatt reactor, research reactor, but in very close vicinity in 4.5 meters. A nucleus collaboration of 8 European institutions. So the detector will be put on the site between 2 reactors in France. The basic idea is to use very small crystals. It will allow one to have very low threshold and excellent energy resolution. And there are 2 types of crystals which will be put. So gram scale crystals, which will be put into cryostat, into active high purity germanium Vito, and into cryostat, and into passive shielding, and commissioning is in this year, and movement to CHU in the next year. Noble gas detectors, two-phase detectors. A two-phase detection technique was proposed by Russian scientists in MEPhI in 1970s, and later it was successfully used in dark matter search experiments. So this method produced charge, which is this method produced. I'm sorry. The produced charge is extracted from the liquid to the gas phase, and of gas detectors, such as the possibility to have proportional or mass and amplification, 3D positioning, and single electron counting, together with the possibility to have the large and a very large mass in the liquid phase. So the progress in setting limits in spin independent proton cross section increased with the use of two-phase detectors. The first proposal was disappeared. The first proposal for CEvNS detection was by Hagman and Bernstein for liquid argon. So the red 100 detector contains liquid xenon, contains 200 kilograms of liquid xenon with 100 kilograms in fiducial volume and 26 photomultipliers inside cryostat. And the data taking run with liquid xenon was at Kalinin nuclear plant in Russia in the beginning of the last year. I would like to emphasize that the background conditions are very stable during on and off. So analysis and current status, there are laboratory tests with liquid argon target. Coherent capital mills. This is a 10-ton liquid argon detector instrumented with 208-inch photomultipliers, and the detector is put in 20 or 40-meter vicinity from PNPI at rest source of Lurian machine of Los Alamos laboratory. So they are taking data now, and the expected count rates is given in this table. You can see that there are thousands of events per year. The neon detector uses the conventional, a few slides, conventional technology of scintillation detector, sodium iodide detectors, which are put inside hermetic envelopes together with photomultipliers. This gives the very high light collection efficiency of 24 photoelectrons per keV, and this allowed to reduce a pinch factor to detect sodium nuclear recoils. So the experiment is out at now on data, and the off data has been already coherent. This is a multi-detector experiment with different targets at SNS, which is a proton accelerator at Oak Ridge National Laboratory in the US. So the detectors are put into so-called neutrino alley in the basement with 8 meters of water equivalent overburden. And there will be next stage, there will be provided measured CEvNS cross sections, and it was the first experiment who observed this process in 270. More details in next talk by A.Konovalov. My conclusion: the experiments on CEvNS detection and study are ongoing. For the moment, CEvNS is reliably detected, and cross section is measured only at PNPI source by the coherent collaboration, and more results are expected very soon. Thank you for attention.
Thank you.
Okay, please. Thank you very much for a very interesting talk. I'd like to ask you about initial proposal from two pairs of theorists in the 80s. So what about the assumption to detect dark matter particles? And could you tell also consistency of these assumptions with consequent observations? Because dark matter particles are not discovered yet.
So it's quite wide question. So as you understand, the idea was to observe very small depositions by detection of number of cells by measuring of magnetic field. So this was very complicated idea, but I don't know why it was proposed so complicated idea. And,
Okay, I think interesting
it's
question. You can
general,
discuss offline. Yeah.
Very general question.
Yeah. Next question, please.
Two questions. First one is about something very fundamental that I'm not familiar with. So for the coherent interaction, the mediator, do we assume it is the standard boson or some exotic particle that in the old literature called pomeron? What do we have a standard theory for the coherent scattering now?
Yes,
that,
standard model theory with the boson exchange. Z boson.
Closer.
With Z boson exchange.
Yeah, that's, I think in your plot you were using Z boson. Is that the standard picture that we are using in this field, or?
I think so.
Let's see.
Yeah, of course, it should be another, for example, Z prime or whatever, but it's beyond standard model.
Yeah.
It sounds clear, but here is Z.
Okay, and a comment that there's also a liquid xenon TBC experiment proposed in China called the RELX. They're proposing to use the Chinese high temperature gas reactor to do that experiment. That is one of the generation 4 reactors. So I think, yeah, just.
Okay, I haven't mentioned.
Thank you.
Because...
Thank you. Another question, yeah, just behind.
Yes, could you go back to page 9? Yeah, I'm quite interested by the first proposal detecting the 7th with gas detector. Here you mentioned, maybe it's not 9. Yeah, this one. You mentioned the threshold is 100 EV is the nuclear recoil or electron equivalent?
It is actually electron equivalent. However, at that time, the experimentalists thought that in gas detectors there will be no quenching, but it is not the case actually.
Well, personally, I think gas detector, so we can detect the nuclei. So I will look into it, but this is a quite interesting method.
Because so how to say, quenching is not only due to disappearing in the bulk, but it is also caused by the process of energy transfer in collisions. So we cannot claim that all energy in gas goes to ionization. It's not the case.
Okay.
Okay,
thanks.
So, yeah. Unfortunately, yeah, we have not much time. Thank you very much again, Dmitry, for talk. So exactly, next talk will be about this coherent experiment. Status of coherent experiment will be presented by A.Konovalov.
Okay. Hello, dear colleagues. I would like to tell you about the coherent collaboration, its experimental efforts, and the physics reach of coherent. So let's start with the collaboration itself. It consists of 21 institutions from 4 countries, and the main goal is look for new physics for non-standard interactions using this process of coherent elastic neutrino nucleus scattering, we call CEvNS. So this process was extensively described in the previous talk by D.Akimov, and it will be the focus of part of my talk. But in the second half, I would also like to tell you about non-CEvNS related activities of coherent, including the measurements of the charge current of neutrino interactions on nuclei, the accelerator-produced dark matter search, and the search for sterile neutrinos at SNS. So we will start with the accelerator facility coherent uses for its studies. It's the SNS accelerator at Oak Ridge National Lab in the United States. And what happens there is that 1 GeV protons are being dumped on the liquid mercury target. The pi minuses, pi pluses are being produced and stopped within the target due to ionization losses. So pi minuses are quickly captured. They do not contribute to the neutrino flux. And pi pluses decay, giving us the first component, mu, which is due to the short decay time is localized in arrival time, and it coincides, the profile coincides with the basically the proton bunch profile, and that's it. So, and this one is the two-body decay at rest. So we have the monoenergetic nu line, which is about 30 MeV in neutrino energy. The second component is from the decay of mu plus, which contains nu E and anti-nu mu. These ones are delayed relative to the prompt component with a characteristic time of mu plus decay, and the energy of these neutrinos span up to 50 MeV. So what is important that at SNS we have like two flavors, nu mu and nu E, right? And two observables, one of which is the arrival time of neutrinos to detectors, and another one is energy deposition. And also the nuclear recoil energies are much larger, about order than at the reactor experiments. Let's continue. Neutrino area, the place where the detectors are deployed. So it's the quite narrow corridor in the building, in the target building of SNS in its basement, and it's nicely shielded from both from the vertical cosmic rays, about 8 meters of water equivalent of construction materials, and about 20 meters of construction materials towards the target. So we're also shielded from the neutrons which come from the target. And there are several detectors deployed right now and were deployed in the past. And if you are interested in how it looks in real life, you can use the virtual neutrino area tour to take a look at this. So let's continue with the description of the first CEvNS detections, which was made with pioneer detectors. The first one was cesium iodine 15 kilogram crystal, which provided us with 7 sigma observation in 2017. And that one was followed by the detection of about 3 sigma by liquid argon detector with a mass about 20 kilogram. And then we have the full statistics of cesium iodine acquired, which gave us basically 12 sigma measurements, which up to date is the most precise measurement of CEvNS cross section, and also the only one above 5 sigma in significance. So, and the final data set, full data set of liquid argon is not yet well published, so there is analysis ongoing, and I would like to say that I think the scale over a year is okay to expect the results from the full exposure of liquid argon detector. This first generation is followed by the successor detectors. First one is the Gemini, the array of high purity germanium p-type point contact detectors, and 6 detectors of this kind are already deployed in the neutrino area with 13 kilogram active mass. The resolution measured with pulsar varies from 100 to 150 EV, depending on the detector, and well, expected threshold is of about 0.54 keV electron equivalent. So this set of detectors has already acquired about a month of beam on data, and right now we have the shutdown for about a year at SNS. So there is not going to be more data for about a year, and whatever result of this first exposure they will be being deployed right now in neutrino ELI is sodium iodine for measurement of sevenths of the lightest nucleus of coherent detectors, the sodium. And this is the ton scale detectors consisting of individual individual crystals of 8 kilograms in bunches in modules containing about 60 crystals. So right now, three modules are deployed and 2 are able to take data right now. So, and the deployment is ongoing. The sensitivity which one expects from this whole 3-ton array is about 3 sigma of 7th measurement per year with a threshold about 13 keV nuclear recoil equivalent. Let's continue with the future hopes of more or less precision 7th measurement following the first light detectors. And this is the successor of liquid argon program, SENS 750, which is going to contain about 600 kilograms in fiducial volume and should provide us with about 3,000 7th events per year. This detector is to have about 128 PMTs coated with TPB for wavelength shifting. So this detector and this activity is funded. The cryostat is nearly complete. PMTs are acquired, and it's expected that it will be placed, deployed in the neutrino ELI by the beginning of 2025. Let's move on with the cesium continuation of cesium iodine program, so to say. So there is a plan to deploy cryogenic undoped cesium iodine, which intended to be like the first cesium iodine detector, but better. And that is intended to be achieved by making it to operate at low temperature, about 70 where the high light yield, and we are going to read out it with the CPMs, which will provide us with no sharing of radiation like in the gas or in the glass of the vacuum tubes, which was the problem for the first detector at some point. So this one is at the stage of the R&D. The detector shape and size are being optimized, and the planned threshold is about 1.5 keV nuclear recoil equivalent. We can compare it to about 9 keV nuclear recoil equivalent. The neutrino interactions on the case you have, let's say, the C prime. This results in just modification of a weak charge of the nucleus. So we just put in the anomalous non-standard of this kind, the couplings to U and to D quarks of neutrinos, and the exclusion limits on this kind of plot look like stripes due to the quartic nature of this weak charge. So, and if you the slope of this stripe only we measure we measure to make some limits on that. Lead with the one is our results. This is the suppression relative to the best known prediction for this kind of process. So again, the lack of neutrons in the final state, which is a thing to understand, and there is no currently explanation for this one. It work for the theoreticians as well. Let's continue with the another activity, which is measurement of neutrino-induced thorium fission, so which was predicted also in 70s. Right now, we have about 50 kilogram of the metal thorium deployed in the neutrino area. It's surrounded by the lead shielding, then with gadolinium water and sodium iodine detectors. And what we want to detect here is again neutrons. So this neutrino-induced thorium fission is going to be accompanied by large number of neutrons in the final state, about 5, 6, 7 neutrons, which are going to be captured by gadolinium and emit gammas, right? Which can be detected by sodium iodine. This one is deployed and taken data. The future of charge current interactions and for coherent is connected to the SENS 750, which should provide us with 300 charge current interactions on argon. And also we would like to consider the liquid argon TPC single phase dune-like for the both of these basically are intended to measure the charge current cross section on argon, which would help to understand what signal from the supernova neutrinos is expected in dune detectors if supernova event happens. Now let's continue with D2O detector. So the largest systematic for the coherent scattering at SNS right now is the knowledge of neutrino flux, which is plus minus 10%. And we want to measure the flux using the well-known process, this charge current on the deuterium, which is well predicted and both measured. We want to deploy 2 modules, 600 kilograms of D2O each. And the one module can push the uncertainty down to 5% with this single model for 2 years of SNS operation. So, and the first model was deployed this summer with D2O. The additional gain from this detector is that we can measure the charge current on oxygen, which is also in the heavy water, right? Okay, let's continue with the SNS schedule. So there is a year-long shutdown, after which the energy of protons is increased and increasing the increasing the power and giving us more neutrinos, let's say. And there is a plan to deploy the second target station at SNS in 2030, which each fourth bunch of protons will be delivered to this second target station. And why is that important to coherent is that right now we have this narrow neutrino alley, and there is no much place for bigger detectors. And for this one, it's being constructed and being planned. So we are working with the administration of ORNL to have a more place, shielded place for a bigger detector. And that affects these plans for bigger detectors, affects our sensitivity for non-standard scenarios. For example, like the accelerator produced dark matter, and the scenarios where sensitive here is, for example, the kinetic mixing, where the pi zeros and eta zeros are produced in the proton collisions with mercury, and there is a d-portal particle which decays to the dark matter like neutral scalars, for example, which scatter coherently on our detectors. And again, this coherency in this energy region allows us to put strong link on this kind of interaction. So the cesium iodine detector, size detector, is right now in this much larger and more expensive detectors. So, and that's going to be better if we have a chance to have, let's say, 10-ton liquid argon detector at the second target station at SNS with the SNS upgrade and the second target station construction. Yeah, and now to the sterile neutrino search, which is not really in the focus of collaboration now. And what we can see there is that we can look for disappearance of both nu E and nu mu for neutrino energy between 10 to 50 MeV on the distances from 19 to 28 meters, something like this. So we can be sensitive to this kind of delta M squared. These disappearance probabilities have, well, 3 angles in them, so we need a on the first target station, we can exclude the significant part of the parameter space allowed by the measurements for accelerator steriles. And one of the things we can do is that with the second target station, we can have one large detector which measures neutrinos from both targets. Well,
a new cesium iodide detector.
Yeah.
What is the energy threshold in terms of the electron recoil?
Yeah, so that depends on the quenching, right? And so let's say I have a number here for the nuclear recoils, right? The quenching is of the order of 10%. Yeah, that's it. There are some discrepancies in the measurement. The earlier measurement says about 10%. Now there are preliminary results which I'm not going to cover, but the scale is this. So 10% larger is about 0.2, right? keV.
Okay, good. And when do you expect the detector to be ready?
The undoped one. Well, I would say about maybe the scale of 2 years, again, 2025 is the right scale, but it's not yet ready. The crystal is not ready. It's R&D.
Okay.
And quenching measurement also.
Another question? Comment?
Yeah.
No, I don't. Okay, thank you very much again for your talk. Next talk will be presented by Dr. K.Kouzakov. Status of tritium neutrino experiment in Sarov, right? Okay,
Thank you.
20 minutes.
Okay, good morning, everybody. The title of my talk is The Status of Tritium Neutrino Experiment in Sarov. So the Sarov tritium neutrino experiment is a part of the research program of the National Center for Physics and Mathematics. The center was founded in Sarov in 2021. So this is the architectural and urban planning of the center. The construction started this year, and by the end of the following year, next year, it is expected that the first laboratory buildings will be ready. And the main goals of the neutrino experiment are the first observation of coherent elastic neutrino atom scattering, in short, CEvNS, and the search for the neutrino magnetic moment. And the key feature of the experiment is the use of a high-intensity tritium neutrino source. It is at least 1 kilo of tritium and possibly up to 4 kilos of tritium. Well, the first part of my talk will be devoted to the physics that will be studied in the Sarov neutrino experiment, namely to coherent elastic neutrino atom scattering and to neutrino magnetic moment. Then I will present the concepts of a superfluid helium detector and cryogenic silicon and cesium iodide detectors. So these detectors are being developed for the indicated purposes. In the end, I will come to summary and outlook. So the major goal of the Sarov neutrino experiment is the first observation of CEvNS, coherent elastic neutrino atom scattering. This process was theoretically predicted by Gaponov and Tikhonov back in 1977. In their paper, they considered elastic scattering of neutrinos on atoms, and using the V minus A weak interaction theory, they showed that at neutrino energies of the order of and less than 10 keV, a region of coherent optical neutrino phenomena exists where the neutrino elastic scattering by an atom as a whole dominates. In other words, the atom behaves itself as a point-like particle in this scattering process. Well, it is almost half a century since the theoretical prediction was made, but so far there is no corresponding experimental observation, experimental evidence. At the same time, the experimental study of CEvNS could provide us a unique test of the standard model neutrino interactions at very low energies, basically at unprecedentedly low energies. Okay, and CEvNS should be compared with CEvNS, coherent elastic neutrino nuclear scattering, that was discussed, what was discussed in the previous two talks. The point is that unlike CEvNS, CEvNS is very well known in neutrino physics and is very actively studied both theoretically and experimentally. And this is the coherence condition for CEvNS. Q, the three-dimensional momentum transfer, and I, the nuclear radius. So when this condition is satisfied, then the neutrino elastically scatters on the nucleus as a whole, as a point-like particle. And this is the coherence condition for CEvNS. It is the same, except that now we have atomic radius instead of the nuclear radius. And when this condition is satisfied, then the neutrino elastically scatters not only on the nucleus as a whole, but also on an atom as a whole. And given that the atomic size is much greater than the nuclear size, it appears that the neutrino energy scale in CEvNS is by many orders of magnitude lower than that in CEvNS. And this is an important feature because it prevents the observation, the study of CEvNS in the CEvNS experiments. I mean, in the current CEvNS experiments. Here's a global map of the current CEvNS experiments. And this experiments can be split into two categories. The first one involves neutrinos from stopped ion beams, and the second one involves neutrinos from nuclear reactors. And both stopped ion beam nuclear sources produce in neutrino nuclear scattering, and thus to study sevens. But these energies are by orders of magnitude larger than those required to observe to study sevens. And thus, the aim of the Sarov neutrino experiment is not just to put a new spot on this map, but to bring the sevens experiments, seven studies to a new level, namely to the level when one can study elastic neutrino scattering, not only on a nucleus as a whole, but on an atom as a whole. And to study sevens in experiment, we need neutrinos with energies of the order of 10 keV or less. And this can be realized using a tritium neutrino source. So tritium decays into helium-3, electron, and electron antineutrino. The energy release in the tritium beta decay is 18.6 keV. And this energy is shared between the electron and the electron antineutrino. So the green curve shows the tritium neutrino spectrum. It is peaked at around 16 keV, and the average neutrino energy is around 13 keV. So this means that with the tritium neutrino source, we can indeed satisfy the coherence condition in elastic neutrino atom scattering, and thus we can study sevens. This is in contrast to stopped ion beams and nuclear reactors, which are employed as neutrino sources in the sevens experiments. However, the problem is that in the case of tritium neutrinos, the atomic recoil energy scale appears to be very low. Electron volts and for the study of cells in experiment, we need preferably light atomic targets, for example, such as hydrogen or helium. And luckily for our purposes, we can use a superfluid helium target that was originally proposed for the light dark matter searches. So the idea of the detection method is as follows. A dark matter particle, okay, in our case, it is tritium neutrino, collides with the helium atom in superfluid helium. And the recoil atom loses its energy when moving in the superfluid. And thus it excites quasi-particles, namely photons and phonons. They propagate toward the surface and induce quantum evaporation of the helium atoms. And the evaporated atoms can be registered by either bolometer or field ionization detectors. So this is the basic idea of the detection method to study cells with the superfluid helium target. And this figure shows the calculated atomic recoil spectra in superfluid helium and in the case of tritium neutrino source. For such a setup as shown here, okay, this is a kind of idealized setup, just for illustration. And the black curve represents the standard model prediction for the sevens case. So that is when we completely neglect atomic electrons in helium and take into account only the atomic nucleus. And if we take into account the atomic electrons, we obtain correspondingly the standard model prediction for sevens, which is shown by this red dashed line. And here you can see a marked feature, namely 0 in the recoil spectrum at around 9 milli-electron volt recoil energy. And this is due to the standard model effect, namely due to the complete screening of the weak nuclear charge by the weak electron charge in the helium atom. And clearly, deviation from this standard model feature will indicate the physics beyond the standard model. And such physics could be, for example, due to a non-zero neutrino magnetic moment, is shown by the why neutrino magnetic moment. The point is that the neutrino magnetic moment and neutrino electromagnetic properties in general is one of the unsolved problems. The discovery of non-zero neutrino magnetic moment will literally open the window to new physics beyond the standard model. Indeed, you see a minimally extended standard model with addition of right-handed massive direct neutrinos already predicts a non-zero neutrino magnetic moment. If we take into account the constraint on the neutrino mass due to the Catherine collaboration, we find that the value is 3 by 10 to minus 19 Bohr magnitude. Okay, this of course very tiny value, but at the same there are various theoretical predictions have already been ruled out by the world-leading laboratory constraints on the neutrino magnetic moment. So these constraints, these upper bounds are obtained from laboratory measurements and from astrophysical observations called atomic ionization channel. I will discuss this channel a bit later in connection with the concepts of silicon and cesium iodide detectors. And the one for solar neutrinos is due to the xenon and T DACMET experiment at Gran Sasso, and the one for reactor neutrinos is due to the JEMMA experiment at Kalinin nuclear power plant. The astrophysical constraints are somewhat stronger than the laboratory constraints, but at the same time, they're model dependent, and therefore they're indirect in contrast to the laboratory constraints. Here, for comparison, I also show the constraints from the CEvNS experiments. And as you might see, they're much weaker. They're by orders of magnitude weaker than the world-leading constraints. And as I will demonstrate further with the coherent elastic neutrino atom scattering channel, we have a potential, if not to discover, but at least to set a new upper limit on the neutrino magnetic moment, which is by 4 orders of magnitude better than the CEvNS constraints, and which is by an order of magnitude better than the world-leading constraints. So with the following concept of a superfluid helium detector. The tritium neutrino source consists of such tubular elements filled with the powder of titanium tritide. The total amount of tritium is at least 1 kilo, and possibly it can be increased up to 4 kilos. Tritium is surrounded with a cubic meter of superfluid helium. The dilution refrigerator keeps helium at a temperature between 40 and 60 millikelvin. An array of transition edge sensors suspended in vacuum above the helium surface registers the evaporated helium atoms. The signal from transition edge sensors is read out by a squid system. So this is the concept. And after 5 years of collecting data, in such a setup, the form of this is time for the we have it only for a small fraction of helium detector cells. This is the idea. Okay, so far I've been focusing primarily on the elastic neutrino atom scattering channel. But suppose that the energy transfer is larger than the maximal kinematically allowed atomic recoil energy. then clearly the elastic scattering channel is closed. Nevertheless, the neutrino can still lose its energy via interactions with an atom, namely via inelastic interactions such as atomic excitation or atomic ionization. These are threshold processes, and in the ionization process, neutrino knocks out an electron from the atom. And this process is also often called elastic neutrino electron scattering or so-called atomic ionization channel. So the atomic ionization channel is of particular interest because it is studied in the experiments that so far have provided the world-leading laboratory constraints on the neutrino magnetic moment. I have mentioned those constraints and those experiments earlier, like Xenon-NT and GEMMA. And in such experiments, I mean in the experiments searching for the neutrino magnetic moment with the atomic ionization channel, one typically studies the neutrino cross-section, ionization cross-section, which is differential with respect to the energy transfer. At small energy transfer values, the standard model prediction for the cross-section is approximately constant. And the idea that the neutrino magnetic moment contribution to the cross-section behaves as inversely proportional to the energy transfer. So thus, the lower the energy transfer, the larger the neutrino magnetic moment effect. Well, these calculations are for the tritium neutrino scattering on a silicon target. Why silicon target? Because we also develop a silicon detector to search for the neutrino magnetic moment with the atomic ionization channel. And as you can understand, for such a detector, it is crucial to have the energy threshold as low as possible. Here is a concept of the silicon detector. It consists of 14 silicon crystal cylinders with a total mass of 4 kilos. They are surrounded with at least 1 kilo of tritium, and possibly it can be increased up to 4 kilos of tritium. The detector operates at a temperature between 10 and 50 millikelvin. So the idea is to take advantage of the Niganov-Trofimov-Look effect. That is when the conversion of ionization energy into heat is amplified by a bias voltage, actually by a high bias voltage. And the heat is measured by microcalorimeters, such as transition edge sensors, which are mounted on each silicon crystal cylinder. So in such a way, we expect to achieve the energy threshold of the detector as low as about 10 eV or even only 1 eV. And after 1 year of collecting data, we may expect the following number of elastic neutrino electron scattering events in the silicon detector within the standard model. And the projected sensitivity to the neutrino magnetic moment ranges from 1 to 1.5 by 10 to minus 12 Bohr magnitude. And this sensitivity is even better than the world-leading astrophysical constraints, not only laboratory, but also astrophysical constraints. Along with the silicon detector, we also developed an undoped cesium iodide scintillation detector to also search for the neutrino magnetic moment with the atomic ionization channel. And it is supposed to be an assembly of undoped cesium iodide crystals with a total mass of 100 kilos, operating at the temperature of liquid nitrogen. So the use of the silicon photomultipliers at the liquid nitrogen temperature for the signal readout is expected to provide the record light collection and the record energy threshold of the detector as low as about only 100 electron volts. And after 1 year of collecting data with such a detector, we expect the following number of elastic neutrino electron scattering events within standard model. And the projected sensitivity to the neutrino magnetic moment is at the level of about 5 by 10 to minus 12 Bohr magnitude. And this is better than the current world-leading laboratory constraints. Okay, I summarize. The tritium neutrino experiment is under preparation in Sarov. It aims at the first observation of coherent elastic neutrino atom scattering in order to test the standard model neutrino interactions at unprecedentedly low energies, and also to search for new physics such as the neutrino magnetic moment. A high-intensity tritium neutrino source is being prepared for the experiment with a tritium mass of at least 1 kilo and possibly up to 4 kilos. A superfluid helium detector is being developed for the observation of coherent elastic neutrino atom scattering by 2032. And it is expected to achieve the neutrino magnetic moment sensitivity, which is by an order of magnitude better than the world leading constraints. Also, a silicon detector and a cesium iodide detector are being developed to search for the neutrino magnetic moment with the atomic ionization channel. By 2026 and 2027, they're expected to achieve the neutrino magnetic moment sensitivity, which is competitive with or even better than the world leading constraints. Finally, our collaboration working on the realization of the Sarov neutrino project involves different Russian organizations, universities and research institutes, and we kindly invite other institutions, both Russian and non-Russian, to join our collaboration and contribute to our neutrino project in Sarov. So thank you very much for your attention.
Questions?
One of your first slides, you showed significant difference of nuclear scattering and atomic scattering, and you showed some equations. Could you explain reasons why it's so different? Or some extra term or in equations? No, previous ones. Previous. You showed equations and also some curves. No, previous.
No equation.
Oh, no. No.
Okay, I understand.
It's like circus, you know. You showed equations. Oh, this one.
Okay.
So you show that there is a significant difference, atomic scattering and nuclear scattering. What about reason? Why? It's probably the reason equation.
So the reason is here. Yeah, this is the atomic form factor. Basically, this is the form factor of Fourier transform of the electron density in the atom. And so this effect, once again, yes, basically this is threat, this is threat. This effect is the effect of complete screening, but not of electric charge of the nucleus, but of the weak charge of the nucleus by the weak charge of electrons. You see? This is the standard model.
Okay.
Yeah.
Other question, please.
Okay. Could you tell if you are going to build the prototype for helium detector and just a big detector out?
First of all, we plan to maybe already this year to fabricate to make the test helium cell detector. Yeah. Oh, this one. So it's only 200 milliliters. And the idea is to test the detection principle itself. Yes, is it working or not? And also to test transition sensors and so on. So
the results are not yet out.
No, we are only going, and maybe if everything will go right, we will do this this year already.
Okay, other question? So may I ask you if you show slide 18, 19, something like 18 or 19? Yes. Yeah. Okay, so you show here some sort of effect, 30 events. But what is the level in this case? What is the level of background? I think signal to ratio is extremely important.
Yeah, it doesn't include signal to background ratio. The point is that we still to investigate to study the background conditions in the low background laboratory in Sarov.
Still, can you say at least some numbers? How many orders of background should be reduced to reach this level approximately?
I'm afraid at this stage, no. I'm unable to say.
Okay, thank you very much again for your talk. And let us move. And we will have last talk of this session, presented by Professor Anatoly A.Serebrov. The result of the neutrino for experiment, sterile neutrinos, dark matter, and the standard model. 20 minutes. Close to the microphone.
Okay. I'm going to discuss result of our experiment in connection with situation with dark matter and standard model extended by means right neutrino. And first of all, let's to see our experimental installation. We use we realized experiment at the Senfrey reactor, which have very compact reactor core. It's very important situation and high enough and power. It's allowed us to study very short oscillation or the short distance. And the advantage of our experiment, this movable detector, ensure energy sensitive. We can measure antineutrino flux from reactor, and from 6 to 12 meters, it's high enough. We compare our situation. Our detector have section 22 centimeter, and as a result, we can measure 24 point for all of this distance and show some bins for energy. As a result, we have matrix about 200 elements, and we can realize the situation when we sum together all information for the same phase. It's extremely important. But in this case, we can organize dependence as function distance over energy, and it just means coherent summing of all results. We can see some dependence shown here, experimental and fit, and according with this red line, result of this fit. At the same time, this point on the plot delta M squared mixing shown here inside this blue triangle, which restriction from the top by means Catherine experiment, from the bottom Dance experiment, and left and right, just inside the gallium anomaly. And the most important result, the recent result of best experiment. Together with best experiment, we can obtain more detailed analysis, because best give confirm own mixing angle with coincidence with result of mixing angle for us, and altogether we have already confidence level even more than 5 standard deviation. No, it seems that we already reach desirable level of 5 sigma, but I would like to say that no sense to be hurry up now, because in principle it's necessary to have the similar result with 5 standard deviation for each of experiment and maybe additional experiment also. Therefore, we realize now upgrade of our old installation and build second neutrino laboratory at the same reactor. And this talk will be after lunch, my colleague Samoilov. You will see our future efforts. But now we can consider situation at present time and what possible conclusion possible discuss if we assume what it will be correct in future and will be confirmed. First of all, there is a situation with sterile mass 2.7 and effective neutrino mass due to mixing with this angle will be 0.8 MeV. Another important conclusion that possible to obtain answer about what type of neutrino we have, Majorana-Dirac, and then more probable it's Dirac neutrino. About Katrin experiment and this effective mass, result of which we discuss here, mass of sterile neutrino and mixing, it means here will be disruption of spectrum just on the distance from endpoint 2.7 eV. And about question Majorana-Dirac, I would like to show the previous plot where the least restriction line from double beta decay experiment. And if in future our point will be still the same position, but even if result of double beta decay will be improved and go down, it means that really nature of neutrino is Dirac neutrino. But we will see now it's only analysis of present situation. But now let's consider situation with cosmology. Maybe this sterile neutrino, which we seems observe in contradiction in cosmology. In principle, there is just similar general opinion, but I would like to show you that it's not correct. First of all, to do analysis in cosmology, necessary build model 3+1. It does not work, but hopefully I have. In this case, necessary to build matrix 4x4, and it was done, but this matrix for vacuum, but we have to understand behavior of this matrix in case of potential inside the plasma. By the way, this suppression completely due to this potential, and for example, for moment 10 to minus 4 seconds, we have a pure state without any mixing, and in time it will be developed like this. And for a moment 10 to minus 1 or 1 second, it will be the similar mixing like in vacuum. Situation with behavior of neutrino energy level will be like this for different neutrino. And what is important that for sterile neutrino, it will be situation when the coupling from plasma will be 10 to minus 3, 10 to minus 3 seconds, or the 2 order of magnitude before when decoupling happened with electron neutrino. It's very important. This is dynamics of this process. And the most important is necessary to understand there is thermalization of this neutrino or not in plasma. For this, we have to consider some equation with generation and destruction of sterile neutrino due to interaction, due to collision, and take into account the expansion of space. Result, it will be very trivial. It will be full thermalization for this parameter. It means density of sterile neutrino will be the same like ours. And after this, with simple result, we can do very simple estimation in according to general relation that 2.7 eV with density like the same with our neutrinos, it will be 5% of energy density of universe. At the same time, it will be about 15% of dark matter. And to explain situation in general, we can discuss the heavy sterile neutrino, but really it's right-handed neutrino. And during the previous calculation, we can see that if mass high enough, necessary use a very small mixing angle. And in this case, decoupling happened extremely early and no thermalization. All points we can see here for heavy neutrino, for heavy right neutrino. And in general, I can demonstrate the well-known and popular picture, but what sense to show this picture? Because now you would like to declare that dark matter is right-handed neutrino. We won't declare that we understand what nature of dark matter. And dynamics I discussed before. Now, in our question, what possible hierarchy of right-handed neutrinos? If we know already that lightest, it will be here 2.7, we can assume very naive hierarchy, the similar like for leptons, electron, muon, and tau, and we obtain additional points here. What is interesting for this plot, but this part is practically free from restriction from cosmological data, besides this one, because here upper level 7 keV, and hierarchy for delta M square like this, we discuss only one simple situation, simple order, normal order, but in principle, we can discuss and in inverse order also. And what we discuss now, in principle, we don't want to say something extremely new. It's a well-known model, a minimal model of standard model with neutrino, just due to right-handed neutrino and necessary add additional elements here. But it's interesting question. What decay time for this neutrino? If neutrino rather heavy, about 1 eV, the lifetime will be the same like time of universe existence. It means as minimum it's upper limit. But for 1 keV, lifetime milliard times more than if compare existence of universe. It means that this type of dark matter will be stable enough. And next question, where we can have doubts that maybe this neutrino in contradiction with cosmological data, I mean astronomical data, astrophysical data. Exactly, I discussed the concentration of gallium-4, and it's well known that concentration depends from number of neutrino, and additional neutrino bring 5% increasing of concentration of gallium-4. Let's consider the situation with astrophysical data, and we can see situations here it's not so perfect. Only one of result, which orange here, just for free neutrino, but you can see here situation something like 3 plus minus 1. Wherefore, it's not good, and we have not information, definite information from nature that a choice already possible to do, decide 3 or 4 neutrinos based on the present astrophysical data. Another very important situation, but necessary discuss the named lepton asymmetry. We know that baryon asymmetry is very small, but if the similar one lepton asymmetry, no sense to discuss this one. But in principle, situation can be completely another. First of all, if there is zero lepton asymmetry, and for example, number of neutrino and antineutrino in this reaction will be equal, the ratio between proton and neutron will be equilibrium at the high temperature, sure. But if not so, we have to introduce so-named lepton asymmetry, also named chemical potential here. It will work the similar like difference of mass, and we destroyed the ratio between neutron and proton. And easy to demonstrate that in this case, due to lepton asymmetry, the concentration of gallium-4 will be decreased, but due to increasing number of neutrino increase, it possible compensation. The main question, what is lepton asymmetry? This is extremely interesting and question which very important, but if, for example, happened, then in future astrophysical data will be like here in average, but lepton asymmetry will be about 5%, the preferable case will be just for neutrino, not for free. But what reason for lepton asymmetry? Nature of this reason at CP violation, it's completely clear. And situation with CP violation now already in very interesting situation. Maybe there is some signal, maybe it's a weak signal because only 2 standard deviation, but extremely important. I mean, experiment C2K and also experiment NOVA. And here it's shown, but on the level 2 standard deviation, there is CP violating effect practically on the maximal possible situation when delta will be P over 2 with minus. And it means if this experiment, this asymmetry in experiment will be negative for astrophysics, or how to say for cosmology necessary, positive, it will be positive result for lepton asymmetry. Now we try to do this analysis in more detail in calculations. I cannot see anything definitely about result, but it seems that asymmetry on the level a few percent is possible. Sure, it's a very interesting question, and the question depends from what order, normal or inverse, and what resonance situation happened when space increase and all this plasma go through resonance position. It's a lot of resonance position, and situation can be changed in time. Extremely interesting task. And now I can give conclusion that we discussed already situation with experiment, and if we combine 2 results, we obtain interesting situation more than 5 sigma, and sterile neutrino 2.7, which correspond 5% of density of universe, and full density of dark matter can be explained due to heavy right neutrino, up to 27%. Later we discussed that in principle now cosmological astrophysical data have not enough accuracy to be sure that only 3 neutrino it's enough for cosmology. And finally, we discussed that CP violation question, extremely interesting and can explain situation in general. Later, I demonstrate here some pictures which we discussed that it's only remind for you. And finally, my general conclusion that now it was shown that still enough room to introduce light, right-handed neutrino in cosmology. And moreover, dark matter can be explained by heavy right neutrino in frame of extended standard model. And thank you very much for your attention. And I would like to say that after lunch, it will be our talk about our efforts to improve our experiment to be sure what we discuss now is really true. Thank you very much.
Thank you very much for your talk. Questions, comments?
Some astrophysical constraints on neutrino mass, but CMB people, WMAP and Planck people constraining total mass of neutrino, which is smaller than this number.
Yes, I understand your question, but our sterile neutrino 2.7 eV, not too much for your question. This is necessary include in dark matter because in time after neutralization, after on the moment about 380,000 years, this neutrino will be already non-relativistic. Therefore, this additional degree of freedom disappeared. Therefore, necessary consider this neutrino like part of dark matter. And therefore, no your question.
Okay.
Hello, thank you for interesting talk. So you showed us results with of combined analysis with best experiments. So just 2 experiments.
What experiment?
Neutrino 4 and best experiment. You showed us more than 5 sigma significance results of this combination, right? Okay. So wouldn't it be more right thing to include into the fit all those experiments that don't see any anomaly to get the like a general result on this?
In any experiment possible, assume not only anomaly, even mistake. Why not? But it's reason what I discussed necessary to repeat and improve experiment. Maybe I don't correctly understand your question.
Yeah, I mean, on this surface with the parameters you showed, there are a lot of exclusion lines from a lot of experiments, right?
If you would like to compare result of our experiment, for example, result of experiment like stereo and prospect, let's discuss.
I mean,
you mean just this?
I mean, just include all those experiments into the fit to get a global result.
Yeah, you mean make a combination or whatever, joint fit, something like that. Question is...
No, first of all, if organized, how to say, some preparation, no sense combine all together what you have. It's not good recipe for women on the kitchen, but in physics the same. Necessary, first of all, realized selection, and only after this combine. I'm all time against global fit method. If you ask me about total global fit, it's not interesting to discuss. But if you would like discuss contradiction, because sometimes it's discussed between our experiment like stereo and prospect. Here there is very simple reason. We measure very long distance and we reconstruct all situation, because if you have attention that oscillation period for our sterile neutrino is 1.5 meter. 1.5 meter, it's already inside the biological shielding. To reconstruct this situation, necessary use so-named, how to say, similar like holographic method. What it means, it necessarily fixed the phase. Just I demonstrate that we select all data with the same ratio of distance and energy. But for both experiments which I mentioned, the distance where we measure only about 2 meters and it's far away from reactor. But in our case, we have information from 6 to 12 meters and reconstruct by means this method. It's different approach. Therefore, I don't want mix together all experiment.
Okay, yes.
It's different method.
Point is clear. Okay, point is clear. So last question, comment. No, no one. Okay, then let us then call speakers for this talk again. And session is over and break is slightly behind